Okay, so this walkthrough, or this discussion, we're going to be talking about asymptotics, specifically asymptotics with multiple recursive calls, okay? And to prepare you guys for this discussion, we have a quick guide, okay? So let's say that we're trying to find the runtime of this function f, okay? When we approach trying to find the runtime of the function f, it may be kind of intimidating because there's like a lot of function calls, like f may do an arbitrary amount of work, okay? So let's try to figure out a plan where we can make these types of problems more approachable, okay? So just like for a quick explanation of like what f is doing, we have like an implicit base case. We're only gonna be executing the function if n is greater than 0. And then we see that in the function f, we call some function g of n, which will do like some amount of work, okay? And then in this case, I'm going to say g of n takes constant time, okay? And then we'll have two more function calls of n divided by 2 each, okay? So the first thing that I like to do when I approach these problems is draw out the recursive tree. So what is a recursive tree? For each function call, let's draw a node for that function call, okay? On the top, we're going to put the input size. In this case, the first time we call the function f, the input size is n, okay? Then inside of the node, I'm gonna put the amount of work that we do in this function call, okay? So for the first function call, we're only gonna be doing constant amount of work because g of n takes constant time, right? If g of n maybe took, I don't know, n time, we would be doing n work here, right? Because the amount of work that we do in f is basically just g by like how I constructed the problem, okay? So let's say that we do one work inside. So the next thing that I want to do is I usually like to draw 3 levels of this recursive tree. After drawing 3 levels, you start to see a pattern, okay? So let's quickly draw a couple more levels. So we see here that the next time we call our function f, the input size is n over 2, right? Okay, so let's say like we have 2 more function calls, each of input size n over 2, and how much work do? We still keep doing 1 work, okay? And then I'm gonna do one more series of function calls. Okay, okay, I'm gonna quickly mute. Okay, perfect. So, and then on these function calls, the input size is n over 4 for all of them, okay? That's the first step. I wanna draw out a recursive tree where for each node, we take note of the amount of work we do for that function call, and we take note of the input size for that function call, okay? Okay, that's the first step. The next step that we wanna do is figure out the work per level, okay? So continuing off the example above, we wanna figure out the total amount of work that we're doing at each level in this recursive tree, okay? So if we notice at the top level, we're doing 1 work. At the next level, we're doing 2 work, right? At this level, we're doing 4 work, right? Okay. So we figure out the work per level. That's the next step. And all I'm doing here, just to reiterate, is I say at this top level, I have 1 work, then 1 plus 1 is 2, then 1 plus 1 plus 1 plus 1 is 4. Okay. And feel free to interrupt me if you guys have questions. Okay, so the next step that we want to do is recognize which sum that we are dealing with, okay? And when we work with these problems, if we look at this column right here, it will always be one of these 3 sums, okay? Or nearly always be one of these 3 sums. I don't want to make like conclusions every time, but nearly always, it'll be one of these 3 sums, okay? It'll either be an arithmetic sum, where between terms we have like the same number, right? We add 1 each time, maybe we add 2 each time. It'll be a dominating sum. A dominating sum is when the last term of the sequence dominates all of the others. And we could say the runtime of the dominating sum is wholly dependent on the last term, okay? So looking at this dominating sum, we see that the last term is n, which dominates all of the other terms, okay? And then the other type of sum, which may be like completely obvious, is if we have a sum of like all of the same term, then the runtime is just like however many of those terms times the value of the term, right? So these are the three types of sums that you guys will see. Okay, and then sometimes you'll need to calculate the height of the tree. Like nearly always, you guys should calculate the height of this tree. Okay, so if we're working with the tree above, what is the height of the tree? This is like a tricky question. And if I tell you guys the answer, you guys can honestly take that answer and apply it to any future problem, and it'll work for this class. Okay, so let's look at this tree. Yeah, it is log n. Nice job. So let's say like we have this tree, and at the bottom, we can see like, let's say this is what n is. Okay, like the first node will probably be like 0, then 1, then 2, then 4, all the way up till n, okay? So I'm just gonna show you guys like a quick proof of why the height of the tree is log n, okay? So let's assume for the proof and for simplicity that n is a power of 2, okay? So if we look at the bottom level of this tree, we can see that this is the same thing as 2 to the 0, or this is basically, let's ignore this one. This is 2 to the 0, this is 2 to the 1, this is 2 squared, and then we can see that the input size is going to be 2 to the h, where h is the height, right, of the tree. Okay, so in order to figure out the height of this tree, we say that 2 to the h is equal to n, and then we see that h is equal to log base 2 of n, right? So we see that if we have a tree that chops by 2 every time, the height of that tree is going to be log base 2 of n. Okay, and you guys don't have to understand like what I just said. Just say that if we have a tree that divides by a factor each time, the height of that tree is log base 2 of n. Okay, so yeah, that's basically all for this mini lecture. And does anyone have any questions?
What's the squiggly n squared and n at the right side of
the
sums?
Squiggly thing? Why did I put a squiggly sign here?
Mm-hmm.
Okay, so the squiggly thing means it's not exactly equal to n squared, but in terms of asymptotics, we can say that it is n squared because we don't care about like the constants. So 1 plus 2 plus 3 plus 4 plus all the way up till n isn't exactly equal to n squared, but asymptotically it is n squared because we can ignore like coefficients, constants, etc. Okay.
So what's the output final answer in this case?
Yeah, good question. So first off, does anyone have any ideas? That's this problem right here. Any ideas?
Would you just add up all the work, or I don't know if you would also factor in the height of it, like of a tree as well?
Oh, okay. N log n. Okay, so the actual answer is n here. Okay, this one's like a tricky problem. Let me quickly explain what's happening. Okay, so if we look at this sequence, we notice that it falls under the category of a dominating sum. Okay, why is it a dominating sum? It's a dominating sum because we know that 1 plus 2 plus 4 plus all the way up to this last term right here, right? The last term is going to be the brunt of the work in the sum. Okay, so the next question arises of what is the last work in this sum, right? If we know what the last term in the sum is, we know what the runtime of the function is. Okay, so let's see here that we can say, if I have this tree, if I have this tree, okay, the bottom of this tree, okay, it's going to be 2 to the h. Okay, if you notice right here, we could say this is 2 to the 0, this is 2 to the 1. The next level will be 2 squared. So the bottom of the tree will be 2 to the height of the tree. Okay, that's like, this is a bit confusing. This is a tricky problem. But if you guys notice that, I'll do it right here. This is equal to 2 to the 0. This is 2 to the 1. This is 2 squared, right? So the number of levels we have, we can say that 2 to the level, right, is the term right here. So the bottommost term in this sum is going to be 2 to the h because h is the height of the tree, right? So if we plug in that value right here, 2 to the h is going to be the last term in the sum. We know the height is log base 2 of n, right? So 2 to the log base 2 of n using logarithmic math is the same as n. Yeah. Nice. So this is tricky. And no worries if like it didn't come. This is a tough problem. Okay. Any other questions? Perfect. So if there's other questions, feel free to, okay. Let's start with question 1 on asymptotics is fun. I named the question, by the way, as you guys can probably tell. Okay, we'll start off by doing just part A. I'll give you guys around 5 minutes. Okay, for the sake of time, I'm gonna go through the first question. Okay, so the first call that we have is g of n and 1. Okay, so this problem is a bit different than the example that I gave in the beginning in the mini lecture, but we could still apply the same techniques to solving it, okay? So for g of n comma 1, I'm gonna create a node and I'm gonna say it's n comma 1 as its input size. And how much work is it doing? It's doing constant work in the function, right? Okay, the next question is how many recursive calls are we doing? We see here that if x is equal to 1, we will have exactly 1 recursive call, and then we will see that the tree will kind of look like this, all the way down till 1 of 0 comma 1. Okay, so the amount of work that we do is simply we do 1 work per level, and there's n levels, so it's n work. Okay, so the next example is a bit more tricky, so let's look at that. Okay, so in this one we have x is equal to 2. So let's draw out the first call. No. Okay, so let me quickly draw out how the tree is going to look. Okay. Okay, so we see here that the call will be n comma 2. Okay, this will have 2 function calls. It will call n minus 1 comma 1 and n minus 1 comma 2, right? And every single function call does a constant amount of work. Okay, so we can see here that this pattern will keep continuing, okay? At this level, we have, let's say at this level, we have 1 work. At this level, we have 2 work, okay? Let's look at 1 more level and then we'll kind of see what's happening, okay? So at the next level of the tree, we will have this call will just call n minus 1 on 1 again, right? Minus 1 on 1. This one will call n minus, this will be n minus 2 now, n minus 2 comma 1 and n minus 2 comma 2, okay? Do you guys kind of see how we have this pattern? So if we keep continuing this pattern, you guys will see that each layer of the tree only adds 1 extra node. And each node does a constant amount of work. So the final sum is going to be 1 plus 2 plus 3, all the way up till the final term of this tree will be n, because that's the height of the tree. Okay, so what's the value of the sum? This is an arithmetic sum with value n squared. Okay. So any questions?
How did you determine that the work was 1 for each level again?
Yeah. So I'll
like inside
slightly,
the circles.
Yeah, inside each circle. So for each function call, we're not really doing any work. So you might be wondering like, what is work to begin with? Let's say that like, I don't know, we had a for loop that goes like for I int I is equal to 0, all the way up till n, right? If I like did like a for loop that executes n times, we'd be doing n work. But all we're doing in this function is we say we have a base case, that's a constant amount of work. Then we basically have a function call, like maybe like 1 or 2 function calls, right? So we see like this function just does a constant amount of work. Yeah, independent of like the input size n, we still do the same amount of work each time. Okay, any other questions? Yeah. Okay, and then one small thing that I want to add in, which I think is important, is what does it mean to do constant work? that means that we do the same amount of work no matter what n is, okay? Constant work doesn't mean that we only do like 2 things. Constant work means that we could be doing, I don't know, 50 steps, but we do 50 steps no matter what n is, okay? So it's like independent of what n. Okay, question. So the first one, sum, is it'll call n comma 1, which will call n minus 1 comma 1, all the way down till 0, 1, and then it'll just be n of those nodes, okay? Okay, so let's move on to part B if you guys haven't already. And for the people that were in part A, I can like answer any remaining questions. Okay, so for this question, we're looking at finding a omega bound that's tight and finding a big O bound that's tight. What this means is we should consider the function when it does as bad as possible, it takes as much time as possible, and we should also consider the situation when the function is as quick as possible, okay? So let's look at the best situation, okay? And the best situation is where we minimize the amount of work that we do. We minimize the amount of work that we do if we minimize the number of recursive calls. We minimize the number of recursive calls if f of x always gives us 1, okay? What that means is we will call g of n, okay? We'll call n comma 1, right? And then what'll this do? Assuming that f of x gives us 1, we're gonna see that it's the exact same thing as the first question from the last part, right? We will do one work, then we will call n minus 1 comma 1. Yes, yes, yes. Okay, so we start with comma 2, good catch. Okay, and then, so the first time we might, okay, so we start off at n comma 2, but then we see that after the first call, if f of x gives us 1, we will have 1 node in the next level, right? Then we will continue just have this like linked list style tree all the way down. And we'll see that in this tree that has n nodes, the amount of work, we can never do better than n, okay? And we can say that that's for both of these parts, right? In both of these parts, in the second part, if f of x gives us 1 back every time, right? It's the same thing as this section, the first section, okay? So the worst case situation, or when it takes as much time as possible, okay? It takes as much time as possible when we do as many recursive calls as possible, right? Recursive calls add to our work. So that's assuming, or that's saying that f of x always gives us the highest possible number. So in the first situation, if we do as much work as possible, f of x will always give us 2, okay? So how this tree is gonna look, it's gonna be very similar to the tree that I went in the mini lecture. It'll be here, and then we will constantly have a branching factor, right, of 2. So it'll be like n at this level, n minus 1, n minus 2, all the way down to the bottom, right? And we can see that the amount of work per level is gonna be 1 plus 2 plus 4, all the way down till 2 to the h, the same as before. We know the height of the tree in this case is going to be n. So the most amount of work that we can do is 2 to the n. Okay, so we can upper bound it as 2 to the n. Okay.
Sorry to interrupt. How can you come up? How did you come up with the 2 to the power of n? Sorry.
Yeah, good question. Okay, so let's consider the situation in which f of x always gives us 2. Okay, if f of x always gives us 2, what's going to happen is we will first call g of n comma 2, which will lead into g of n minus 1 comma 2, g of n minus 1 comma 2, right? And then it'll keep creating these other recursive calls, right? And then since we have this, like, we keep splitting by 2 every time, we see that the amount of work that we're doing at each level goes 1, then 2, then 4, then all the way down till the bottom level, which we know is where the majority of the work is doing, because this is a dominating sum, right? So since the bottom level of the tree is where the total amount of work is doing, we just need to know how many nodes are at the bottom level, which is 2 to the height of the tree, or 2 to the n, because the height of this tree is n. Does that kind of make sense?
Yeah, it does. Thank you.
Okay, perfect. So we can see in the next problem, if this is n here, the only thing that's changing is now instead of having like 2 branches, now we're going to have n each time, right? So what that means is we'll have n branches, okay? And then we'll have, right, another n at each level, okay? So that's the second part. And in this part, we see that we'll have 1 and then n, right? I'm looking at the second situation when it's g of n comma n. We'll do 1 work at the first level, n work at the next level. Then we'll be doing n squared work here, right? Then we'll be doing all the way down to the bottom where we'll do n to the n work, okay? Because each node branches n more, okay? And in response to the question by Jason, a dominating sum isn't always equal to n. A dominating sum will always be equal to the last term in the dominating sum, okay? What that says is if we have the sum of 1 plus 2 plus 4 plus all the way up till 2 to the n, right? Since 2 to the n is the last term in the sum, 2 to the n dominates, right? Just in the examples that we looked at before, we saw that it was like 1 plus 2 plus 4 all the way up till n, so n dominated. But in this example, since 2 to the n is the last term, 2 to the n dominates, okay? Okay, any other questions? Questions? Okay, sorry, I kind of rushed it, but the next problem is really, really cool. So let's get started on the next question. And okay, if you guys don't have questions if you guys have any questions on this one, I'll answer them in the chat. But otherwise, let's move on to flip-flop, okay? How flip-flop works is, this problem is very, very hard, by the way. It's a very tough problem, okay? So I'll answer the questions in the chat after I just quickly introduce the problem. So we have some function called flip, which will go in this for loop. And we know at one point in the for loop, g of I comma n will equal I. In other words, at one point in this for loop, this condition will be true. And we will call flop of I comma n, and then the function will return, okay? So we're gonna look at the runtime of flip when flop is defined as this, and then there's one more, okay? So given how flop is defined, we need to figure out what the runtime of flip is in the best and worst case, okay? So good luck, this is a tough question, you guys got it. And then I'm gonna answer some questions in the chat. Okay, hello. So this question is like really hard. And for the sake of time, I wanna go over the parts. I understand that like some people have to go, but I will finish by Berkeley time. Okay, so I'm gonna walk through like the solutions for these 3 parts. If you guys have any questions, like please save them till the end just for like the sake of time, because I know some people may have class at 5:10, but I'll definitely stay after for like the next like 10-20 minutes if you guys have questions on any of the previous parts and this part. Okay, so let's get started. Okay, so if we have flop defined as follows, what's gonna happen if we call flip of n, okay, is we will go inside this for loop, okay? Then when I is equal to 1, we have a decision to make. Either g of 1 comma n can be true or it could be false, okay? So let's consider both possibilities, okay? Let's say this is the true possibility, and let's say this is the false possibility, okay? So if it's false, we still have n minus 1 steps to go, right? There's still n minus 1 more steps to go in the for loop, okay? Until like we're completely done. Actually, if you want to be really precise, there'll be like n minus 2 more steps to go in the for loop, okay? If we choose the possibility where g of 1 comma n gives us true, what's going to happen is we go inside here, we call flop on when I is going to be equal to 1 and n is going to be equal to n. What's going to happen here is that'll call flip of n minus 1, okay? So the weird thing that's happening in this situation is that if g returns true or g returns false, we find ourselves in the same situation, okay? This is like kind of trippy, but try to prove to yourself that either way I go, I still have around n minus 2 more steps to go till I finish, right? Either choice I take, it's still going to take me n minus 2 steps to go until I'm completely done, okay? And if you guys continue this pattern, you'll see that no matter what happens with g, it'll always take us n time, okay? So for this problem, I recommend playing with an example and you guys will see that pattern. So this is a weird situation when the best case and the worst case is n. And if this didn't come easy to you, play with an example, you'll see that's the case, that each time, like each step that you take, it'll keep going, like we'll keep going down by 1. Okay, so let's look at this next part. Okay, now it's getting trickier. So what's happening here is that flop is going to take the minimum of a and b minus a, okay? So what is a and b minus a? A will be equal to I, right, at some point in our while loop, and b will be equal to n, okay? So if we look at, so if we take the minimum of the two, we have I and n minus I, okay? So we're basically taking the minimum of I and n minus I, right? Okay, so let's look at the best case possibility. The best case possibility is if we do as little work as possible. We do as little work as possible if when I is equal to 1, the first time we come here, this evaluates to true, okay? G returns true when I is equal to 1. What happens next is we call flop of 1 and n, okay? What's gonna happen here is that 1 compared to n minus 1, 1 is the minimum, right? Because what we're doing here is we take the minimum of I and n minus I, right? And then we call flip 2 times on the minimum. So what's going to happen is we'll call flip on 1 and we'll call flip on 1, both of which just terminate immediately. So in the best case, it takes us constant time, okay? Looking at that more robustly with like our plot, we see that if we have n, then we will have 2 calls to 1. They'll terminate immediately and we have constant time in the best case, okay? So in the worst case, we do as much work as possible, okay? And intuitively, it may be hard to stumble upon like what I'm going to show you guys, but we kind of want to maximize the minimum of these 2 values, okay? Because we know that when we do our 2 recursive calls, the value for n will be the minimum of I and n minus I. Okay, I'll say that again because it's very important. When we do our recursive calls to flip of low, the value of low will be the minimum of I and n minus I, okay? We want to avoid getting to the base case. To avoid getting to the base case, we want to maximize how big low actually is, okay? Low is maximized when I is equal to n over 2, right? If we enter like the if condition exactly halfway, we know the minimum of n over 2 and n minus n over 2 is n over 2, right? And if we keep doing this every single time we call flip, what's going to happen is we'll get the following tree, okay? We'll get a tree where we have n over 2. Okay, we'll have n over 2 as the first level or the second level. Then we'll have nodes here of values n over 4, right? All the way down till we get to the bottom of our tree, okay? The runtime of this, well, first we need to figure out how much work each call does. In order to enter the if condition, when I is equal to n over 2, we must have completed n over 2 steps to get there. So each function does n over 2 work, right? So then this level will do n over 4 plus okay, n over 4, right? And we can see that the next step in our tree recursion path is we need to figure out the work per level. The work on the top level is n over 2. The work on the next level is also n over 2. And if we continue this pattern, we see the remarkable discovery that the amount of work for each level will always be n over 2, okay? So the total runtime is n over 2, because that's how much work we're doing per level, times the number of levels, which is log n, okay? So in this situation that maximizes how long it takes, the worst case is n log n, okay? So this is pretty tricky, and I'll take questions about this part at the end. Okay, we're almost there. There's 3 minutes. You guys can do this. So this last part is probably the toughest part, and this is a really, really hard problem. So no worries if the other parts didn't make sense, because hopefully after watching and after the questions at the end, it'll come together. Okay, so in this last part, we're gonna call flip on A and flip on B minus A, okay? It's very similar to this section right here. Instead of calling it on the minimum both times, we call it on A and the B minus A, okay? So let's just see how that tree is gonna look. We will have n at the top, then we're gonna have maybe n minus I here, and then we'll have I here, right? Do you guys kind of see that? That's how the tree is gonna look. Let's say that we do 5 steps, and then we decide to enter the if condition when I is equal to 5, right? What'll happen is we'll call flip on 5, and then we'll call flip on n minus 5, right? So I just decided that I'm just playing around right now. What happens if we enter the if condition when I is equal to 5? This will be the resulting recursive calls, okay? Then let's just look at one more iteration to see what else can happen. Let's say we enter, I don't know, when I is equal to maybe 5 again. We'll have n minus 10, then we'll have n minus 5. Okay, n minus 5. Yeah, anyways, okay. So the gist of that's what I'm trying to show here is the amount of work per level will always be n, okay? You guys kind of see that? The amount of work that we're doing per level in this tree will always equal n, okay? Let's say that this is I equals 5, we decide to enter. And let's say we decide to enter at I equals 5 again. We will have, I think, n minus 5 minus 10, and then we will just have 5 here, right? Okay, so you guys kind of see how the amount of work that we're doing will always be n, okay, at each level. And the maximum number of levels that we can have is n, okay? So we can have a maximum of n levels, max number of levels. And if we always do n work per level, we can never do more work than n squared, okay? I still haven't shown you guys how we got to an n squared solution, but this is just showing that we can never do more work than n squared, okay? And you guys should also notice that we can never do less work than n, okay? Because we have to do at least n work once, right? Okay, so all I've done so far is I've said we can never do more work than n squared, and we can never do less work than n, but I still haven't shown you guys how we actually have an n squared and an n solution, okay? So let's say, I'm gonna quickly move this to the side. Okay, let's say that we always enter the if condition at the last possible time, okay? How that's gonna look is we'll have n here, then we'll have 2 recursive calls, we'll have 1 to 1 and 1 to n minus 1, okay? So what I'm gonna say is, let's say that we take as much time as possible and we enter the if condition at the last possible time. These will be the resulting recursive calls, right? It'll be right? It'll look like this kind of tree, okay? And if we look at this tree, the runtime is that each level in the tree, this level will do n minus 1 work, this level will do n minus 2 work, this level will do n minus 3 work. So the total runtime here is the sum of all the levels. We see that this sum is n, I'm just gonna say this is n for simplicity, plus n minus 1, plus n minus 2, plus all the way up till 1. The value of this sum is n squared, okay? So we can see in the situation when we enter the if condition at the last possible time, every time we will get this tree-like structure, and the total amount of work that's done is it's going to be equal to the sum per level, which gives us the arithmetic sum of n plus n minus 1 plus n minus 2 all the way up to 1, which evaluates to n squared, okay? So we know we can't do worse than n squared because that's what I showed you guys earlier, okay? So we know that this is indeed the worst case, okay? Okay, I'm almost there. Hang in with me. We're almost done. Okay, the best case situation is if it minimizes the amount of work that we do, okay? The best case is gonna be if we enter the if condition at the earliest amount of time every time, okay? What that's gonna say is when I is equal to 1, we enter the if condition every single time. How that's gonna look is the only thing that changes here is now we do constant work for each function call because we enter the if condition immediately. Okay, if we enter the if condition immediately every single time, we have the same tree-like structure, but the work per node is different. Instead of doing n work per node, now we do constant amount of work per node, and we see that we have n of these nodes, basically, and then the total runtime is n in the best case. Okay, sorry if that's a lot. I wanted to squeeze it in before Berkeley time, but okay, there's probably a lot of questions, so ask away.
Can you explain the part B one more time, please?
Yeah, okay, part B. So,
yeah, thank you.
Yes, okay, the best case of part B or the worst case, or both?
Oh, so hold on, sorry. Before the part B, I didn't even understand the part A though. Sorry. For the first part, for the part A, you were saying there are two cases, either true or false, right?
Yeah.
So when I don't really understand when the true case happens.
Oh, okay. So like what I mean by the true and false case. Okay.
Yes.
Okay, I'm gonna quickly get rid of this. Okay. So I'll go a bit slower now because I'm over time, so might as well just like go slower. Okay. So let's say that we call flip on 10. Okay. What's gonna happen is we will enter this if condition and we'll ask ourselves, does g of I of n equal I? And we know this is true at least once. So let's say that this is true. What's gonna happen is we will call flip of 9. The reason we call flip of 9 is because we call flop of 1, 10. Okay. So yes, okay, this is a good question. Okay. The reason that like I can use this example, a flip of 10, is because this base case doesn't really matter what number I choose here. I can say n is equal to 0, okay? And it's the same exact thing. So for simplicity in my example, let's just assume the base case is 0. The reason I can say the base case is 0 is the same exact as like less than 100 is because if we look at n getting really, really big, that's like how we deal with runtime, right? We only care about n getting really, really big. It doesn't matter if like we miss the last 100 steps, right? So like the value of the number here doesn't really matter. And for this example, let's just assume it's 0. That was just meant to be like a trick to make sure you guys understand. But yeah, okay, good catch. So in this situation, if g of I comma n gives us true, what's gonna happen is we will have a call to flip of 9, right? If it gives us false, we still have 9 more steps to iterate in our for loop, okay? So in both situations, you see that like we keep continuing this pattern. Eventually, no matter what path we take, it'll always take us 10 steps, okay? Like here, after, if we have 9 more steps left, we can either call flip of 8 or we have 8 steps left, right? So no matter what like happens with the G, we will always take the same amount of time, okay? Does that kind of answer the question?
Yeah, it does.
Okay, so this is a tricky problem. So no worries, like if it's still like a bit confusing. Okay, any other questions? I'm sure there's a lot of questions.
We can't go over part 2 as well.
Yeah, I can go over part 2. Okay, so let's go over part 2 a bit slower this time. Okay, so in part 2, okay, do you have a question about the worst case or best case or both?
Actually, both. Thank you.
Okay. So when we think about the best case, we want to minimize the total number of steps that we're taking, okay? To minimize the total number of steps that we're taking, if we enter this if condition immediately, right? If when I is equal to 1, we enter this if condition, we'll see that we call flop, okay, of 1, n, okay? After calling flop of 1, n, we see this has 2 calls, both to flip of 1, okay? So we see that in the situation that we enter the if condition immediately, all we're doing is calling flip of 1 twice, and both of these calls will give us constant time because they'll hit a base case, okay? And we can make the base case 1, sure. Okay, both of these will like hit the base case, and then they'll terminate. So in the best case, we will take constant time, okay? In the worst case, on the other hand, the idea is we will enter the if condition when I is equal to n over 2, okay? When we enter the if condition, if I is equal to n over 2, we will get the following tree, okay? We will have n as the first input, then we will have n over 2, okay? And these are calls to flip, okay? These are all calls to flip. So if we enter when I is equal to n over 2, what's gonna happen is that low will be equal to n over 2. And if we call flip on n over 2 and a flip on n over 2, we will have the following recursive tree, right? And if we look at this recursive tree, we see that at each level, we go n over 2, n over 4, right? And the next question arises is how much work are we doing per node? Well, each node, all it's doing, it goes exactly up till n over 2 steps, and then it terminates. So if each node does n over 2 steps, right, we see that it'll be n over 2 at the top, that's my bad. Then it'll be n over 4, because n over 2 divided by 2 is n over 4. And we see that each level does n over 2 work. And how many levels are there? Log n. So we do n over 2 work for log n levels, giving us n over 2 times log n. Then we can remove the divided by 2, and we simply get n log n. And then if you guys want to consider like what happens if we exit the while loop or exit the for loop at the very end, like let's say, I don't know, consider another possibility. Let's say that we exit at the very end when I is equal to n minus 1. What'll happen is that low will be equal to 1, and we will still get these 2 function calls, okay? So in order to like maximize the input to the next calls to flip, we want to exit when I is equal to n over 2, right? Yeah, so that gives us the worst case because that takes as much time as possible. Okay. So any questions on like part B? Okay. Does anyone want another explanation on part C?
That would be nice if you don't mind.
Okay, let's do it. Yeah.
I'm still understanding why it's n over 2 per level. Like, what's the difference between this and when work is just 1 per node?
Yeah. So, like, where do we get the n over 2 work come from?
Yes.
Okay. So every time we call flip, what's going to happen is we will enter this for loop. Okay. We'll enter this for loop. So the next question is, how many steps do we take in the for loop? We're going to keep executing this for loop until I is equal to n over 2, right? Because we've realized that setting I equal to n over 2 maximizes the value on the resulting recursive calls to flip, right? So if we only enter this if condition when I is equal to n over 2, we have to take n over 2 steps to get to this spot. So that means every time we call flip, we will take n over 2 steps, I will become n over 2, then we call flop of I being equal to n over 2 and n. Does that kind of make sense? Okay, perfect. So, okay, let's continue with an explanation on the last one, a little slower. Okay, so with this last part, let's get rid of this just to make it cleaner. Okay, I'm gonna show you guys the answer and then I'll prove to you why it's like the answer. So the worst case situation for the final part is if we enter this if condition at the last possible time. Okay, if we enter this if condition at the last possible time, what's gonna happen is, let's quickly play that out. I'm gonna get rid of this. Okay, so just to reiterate, if we enter this if condition at the last possible time, we're gonna have the initial call to flip of n, right? Then we will have two recursive calls, okay? The first one, actually we'll first call flop of n minus 1 comma n, right? If we enter this if condition at the last possible time, we'll call flop of n minus 1 comma n. What this will do is it'll call flip on n minus 1 and it'll call flip on 1, right? So flop of n minus 1 comma n leads to two recursive calls, okay? Both, one will be n minus 1, one will be 1, right? Because we call flip on n minus 1 and we call flip on 1, okay? So we see here that if we keep exiting this for loop at the last possible time, we will get the following tree-like structure, where at each level, we have two recursive calls, one of which just kind of dies here, and then the other one keeps going, okay? So the question is, how much work is happening in this weird tree? If we look at this tree, we see that the amount of work for the first function call is we needed to take n steps to get to the very end, right? To get to the end of the for loop, we needed n steps. Then we needed n minus 1 steps, n minus 2 steps, all the way down to 1. So the total number of work that we're doing is just going to be the sum of these nodes, right? The sum of these nodes will be 1 plus 2 plus 3 all the way up till n, which gives us the sum of n squared, okay? So in worst case, we take n squared. And the reason why n squared is the worst case is because if you guys think about it, we cannot do any more than n squared work, okay? Any recursive tree that we try to draw out, because there's many, many possibilities here, any recursive tree that we'll draw out will always do n work per level, okay? And the maximum number of levels is n squared. So the maximum amount of work that we can possibly do is n squared. Yeah. Okay.
Thank you.
Yeah. And then the best case situation is if we enter the if condition the first time every time, and that gives us the same tree-like structure, but we do constant work at each node, giving us the runtime of like n. Okay. So can you give a good example for the second part? Wait, can you elaborate, Kushi, on the question?
Yeah, so like you were just talking about like the n divided by 2. So like, can you just give like two integers that I can like try out myself so I can see how it like maximizes it?
Oh,
Or the second part.
Yeah. Okay. Let's say that like we always choose like a as n over 2, and then b has to be n, just because like that's how the function gets called.
Okay, that makes sense. Thanks.
Okay, and then so Patrick also brought up this idea of like what's the difference between worst case and best case, and what's the difference between like a big O and omega. Okay, so I'll quickly talk about what it means to have a worst case runtime, what it means to have a best case runtime, and why we can use a theta bound for a worst case and why we can use a theta bound for a best case. Okay, so when we think about the worst case runtime, we're allowed to use a theta bound because we're only considering specific instances when I call my function and it produces the worst case behavior, okay? I'll say that again because this is like pretty confusing. When we look at the worst case runtime of a function, we're only considering the situation that produces the worst case behavior, okay? So if we look at, I don't know, any one of these function calls, like let's look at this one right here. We know that the worst case behavior happens when g of I comma n always like exits at the last possible time, right? So if we think about the worst case behavior of a function always takes the same amount of time. If that's true, we can give a theta bound on the worst case. Okay, I'll say that again because it's like kind of confusing. If the worst case behavior of a function always takes the same amount of time, we know there's no ambiguity here. The worst case is always n squared, so we can give a theta bound on the worst case. And I can use the same logic on the best case. Okay, that's the reason we can use a theta bound on the worst case or best case. It's because we're only considering the specific instance of calling that function where everything goes as badly as possible, right? In the situation where everything goes as badly as possible, the function always takes the same amount of time, n squared, okay? So that's why we can use a theta bound for n squared, or for worst case. And then like, how does big O and big omega fit in? For most situations, the big O will be equal to like the worst case behavior. So for the sake of this class, it's easy just to think about like, you can set big O as like the worst case behavior, but in certain other functions, we may not actually know like how bad the worst case behavior is. In these functions, it's easy to see that like the worst case always takes n squared, but if we don't know like what the worst case actually is, we may need a big O bound, okay? So that's like the quick gist on worst case, best case, and big O. Okay, any other questions? Okay. Okay, so I think if nobody has any more questions, I'll quickly go over the part up here about 2 to the n, because I think that was like one more part of confusion. Now, good question. Are exam questions this hard for asymptotics? This problem's like a bit harder than like an exam question that you guys will see. So don't worry if it was difficult. Yeah. Hopefully you guys like thought it was cool. I enjoyed it, like solving it myself. Yeah, I'm sorry if I made you guys suffer. Okay, so I'm gonna quickly explain why this is 2 to the n because some people had confusion, and then after that we can probably call it. Okay, so let's quickly go over when this 2 to the n behavior occurs. Okay, looking at this function, what's gonna happen is we will call g of n comma 2, okay? What this will do is it will call g of n minus 1 comma 2, and it will call g of n minus 1 comma 2 if f of x gives us 2 back, okay? And we're considering the worst possible situation, so we're gonna assume that f of x always gives us 2 because that's like the worst case behavior, right? If f of x always gives us 2, we do as much work as possible, right? And that's like what we want for a big O bound, to find this worst case behavior so we can bound it, okay? So we see here that if we have this structure, we have this branching pattern, okay? So looking at the familiar recursive diagram, we see that it will look like, okay? We will have n, then we'll have n minus 1, n minus 2, right? And then we'll see that this pattern will continue all the way down to the last layer at value 1, right? Or at value 0, sure. Okay, so the question is how much work is happening in this tree? We know that each function call does a constant amount of work. So what we're actually using is, we see that we do 1 work here, then 2 work, then 4 work. So the total amount of work is increasing by double each time. So we see that it's a dominating sequence where this last term on the end is what constitutes the runtime of this function. So what is that last term on the end? We see here that we can say that the work per level is 2 to the L, okay? Where L is the level that we're on, okay? So the last level will be equal to H, where H is the height of the tree. So 2 to the H is the same as 2 to the N because the height of this tree is N. And we see the last term in the sum is N. So our final runtime is this sum, which evaluates to the last term since it's a dominating sequence, and that's 2 to the n. Phew, okay. So I see one more thing in the chat. Okay, so that's all for this discussion. I'm sorry if you guys had more questions and we didn't get time. I understand that this might have been like a really, really hard discussion for you guys. So as you guys like walk away from this, know that these problems are really hard, and like you guys will keep getting better and better with practice at approaching them. So yes, and yeah, thank you guys for coming. I'm sorry if it was a little confusing at times. So for the lecture notes, I can email them. Actually, let me think. I can make an ed post about them so everyone can have access. That'll be nicer. Yeah, ed post will be good. Okay, yes. Thank you guys for coming and have a good one.
Thank you.
Yeah, you guys